Hello explorers and welcome to another video. Today I'm gonna talk about fonts. And I have been hobby coding a little bit. I've been creating something in my spare time just because I had a couple of days where I did a bunch of work at work that actually didn't add any coding knowledge. I didn't write any code or anything like that. So I felt that I needed to do something. So I read up on the font 1 type and how you actually encode and work with that. So I read the specification and then I implemented a solution for it so I could actually create my own font 1 files. So now I can take a PDF, read a bunch of different other fonts and convert them into font 1 fonts. In some cases I might lose some information and I haven't really done any work to map the font back to where it actually should show on the page, but I can write it into a PDF again. I can also write it to a file on disk and open it in FontForge in order to look at it. So font 1 is sadly one of the fonts that have been deprecated. So Adobe will no longer create any font 1 files. They still support reading them, but their tooling has removed that functionality as of 2021. I wasn't really aware that that font was deprecated. I see it all the time. So I think it's interesting to actually know how the font is constructed and what different part is in it. So let's switch over to my screen here and talk a little bit about fonts. So first off, the font is encrypted. And that sounds a little bit strange because it's readily readable by anyone. But there is some parts that is in pure ASCII, so you can open the file and just read the font. And some parts are private, which is encrypted once or twice in order to hide the information. It's not really to make it impossible to read because the decryption and the keys are known. So one part of the file is the private part, which is encrypted with this EExec key, which is just a word here, 55665. And then you have a char string, which is each character, and those are encrypted by 4330. And then you can have a bunch of random bytes that you put in the beginning of your encryption in order to have some kind of initialization vector, and the default is 4, but you can put as many as you like there because the encryption function will have it defined in the structure how many it is, so you can remove them afterwards. So I have an encryption buffer here and I have a used flag because I don't want to use this encryption multiple times when the initialization vector is not reset. So if you have something that are dependent on starting at a specific position, then you don't want to end up in a state where you reuse it. And then I have this boolean to say if I'm gonna encrypt or decrypt. Then we have a couple of things that are from this documentation here. We have the R, where we will put the key that will be used for the encryption. We have an N, which is the number of random bytes. And then we have C1 and C2, which is two constants that are also specified in the documentation. Then I have a hex array here, and this is mostly just used in order to go from byte to hexadecimal and hexadecimals to bytes, because the format will either store in binary form or hexadecimal. So when we create this kind of object, we will say if this is a char string encryption or an EExec encryption, and if we should encrypt or not. And we can also supply the number of random bytes if we want. So the only thing we do down here is set the encrypt flag and set the right key that we want to use for the encryption. Then I have a function here that will put the data in. So if I send in some data and I should encrypt it, then I will take the data, which is a string, and use the ISO 88959-1 in order to read the bytes. If you use UTF-8 here, it will not get the correct bytes, so and the encryption will not work. And US ASCII didn't work either here. I guess US ASCII is a more narrow space. And then I can also get hex bytes, because in this case, when I decrypt something that was encrypted, it is encrypted into hex in the cases that I was looking at. In the future, I might extend this function so I can actually write even bytes that are binary, because the binary format doesn't use hex, of course, the binary format of the font 1. And then I also have a function here where I can just set a bunch of bytes, and if I should encrypt, so here we set the bytes up here, but I can set the bytes directly. And if I do that, if we should encrypt something, then I will start a random to create a bunch of random data, and then I will create an encryption buffer here that is n bytes plus data buffer bytes long. So this is the full buffer that I want to write to. So these that I want to be random at the beginning, and then I just create random bytes over everything. Doesn't really need to be that way, but I do that anyway. Then I will copy over the data bytes from index 0 over to the encryption buffer at the start of this n, and then the full length of the bytes, so everything. So that will copy all the data over to this encryption buffer after the random bytes. And if I'm gonna decrypt, the random bytes are already there, so I just set into the encryption buffer. Next up, we have two functions that are pretty much copied from the internet. So these are hex to bytes and bytes to hex. And they are pretty standard functions, and yeah, I didn't feel like writing them myself, pretty much. And then we have the result here. So I can get the result and can either get it in binary or not. And if we have used this encryption already, throw an exception. I don't want you to reuse it. So we will go through the encryption buffer. We will pick the first character here, or the first byte. And then I will take that byte and XOR it with the first 8 bits of the key, and then store it back in the buffer. And if I should encrypt, then I want to have that what I actually wrote back, because that is going to be used for the next iteration. And if I don't want to encrypt, I want the original encrypted byte as something that I want to use to create the next key. And creating the next key is using this algorithm. It's standard and the same algorithm that I show in the specification. So you will take the key will be equal to the newly encrypted byte plus the key that was in the state now times the first constant plus the second constant. And then we need to make it into a word again. So we will modulus that operation with the 16 bits here in order to remove anything that will be too large. So now we have a new key, and we will go on again. So the important part here is always to use the encrypted character for both encryption and decryption when you change the key up. So this was something that tripped me up during the implementation. I just took the value up here or down here, and I weren't able to encrypt and decrypt. And then if I want to encrypt, what I want to return is in the binary case, just a string of the encryption buffer, otherwise I will return a bunch of hex. bytes, and if I'm decrypting, then I take this return array and copy off these n bytes that are here, remove those, and then I will return the string here. So that's pretty much what I'm doing in order to encrypt and decrypt stuff. So let's go to the char strings. We go from in the inner sanctum and out to the font file. So in order to write a character, we have first off a bunch of characters that are not defined. So we need some way to set up those, and those have always the name of not defined. And then we have a bunch of these bytes where different operations. We have an H stem, V stem, we have a V move to, so that's a vertical move to, and we have a horizontal move to. These are values where one of the axes is 0. Then we have a relative LineTo, so that takes 2 parameters that are relative to the point where you stand now. So let's say that you want to go from 1, 1 to 5, 5. Then the relative line would be 4, 4, because you will go from 1, 1 down to 5, 5. So that's interesting. Then we have a horizontal line 2, vertical line 2. We have an error curve 2, which is the Bezier curve that we will use. We have a close path. When the path is done, we can call substrings. I haven't implemented that yet. We have a return from a substring. We can extend with more functionality. So there is a bunch of functions that use 12 and an extra byte in order to do stuff. We have this HSBV, which tells you where the starting position will be. And then we have the end characters. The character is done. Relative move to. We have a horizontal move to. And then we have VH curve to and HV curve to. So those are different variables. I haven't used these. I've just defined them here if I want to implement them in the future. Each character, I have a capacity here of 60,000 bytes that I can write to. Could have a larger buffer, but I haven't run into a character that is that large. So I find that's a reasonable amount. Then I want to keep track on where I am in order to do these relative calculations. So the current X and Y is something that I use heavily here. And we have a name of this character and an index of this character. So when we create it, we will give it a name and an index. We will set those down here. We will set the current position to 0, 0. And I will set the current buffer to 0, 0 as well, if it's defined, this character. If it's not defined, I don't want it to have any bytes in it. I want it to be empty, but if it's not defined, if it's defined, I want the starting position. Then we have a very interesting function here, int2bytes. So they wanted to store large stuff in smaller spaces, and they wanted some way to figure out how can I store just 1 byte when I have a very small value. And the way they did it is a little bit cool, actually. So they take a value here. If you have a value that is either 107 or below, or minus 107 and below, if you have these kind of values between those, you will add 139 to the value and store that. Which means that you have a bunch of values, 32 of them, that is before these values, which means those are the bytes that are control characters. So if you have anything from 0 to 32, that is some kind of function. And so that could be read like that. That's what we defined up there. And then we have the value here that starts at 32 up to 39. 139. And then they wanted to store even larger values, of course. So if you have a value that is 108 to 1131, they have calculated this a lot, Then you will do it like 2 bytes. And you will start at 247 and find a divider that you will add to that. So finding a value and decrypting it will take the first byte minus 247 will be your multiplier. So we'll multiply that with 256. And then the second byte is the remainder that you will add to that. So that's pretty clever in order to get a really large value. So what we will do in order to store that value, of course, is remove the first to 108. So we will have the value without this buffering in the start. Then we will calculate the remainder. So that's just a modulus operation. So we will get a remainder here. That's the second byte. We will remove that from the value and then divide it by 256. And we should get a value here, either 0, 1, 2, 3, maybe 4. No, 1, 2, 3. So that is what we will put in those 2 bytes. If we have a negative value, on the other hand, we need to do the absolute value of that, and then we do the same operation here, but we store it from 251 until 254. So the first byte, if it's in that range, we know that this is the negative value up to minus, or down to minus 1131. So these are quite interesting calculations. And if you want to store something that is even larger or smaller, then you can store a full integer as 4 bytes. So you will set just a byte 255 and then put an integer there as the second 4, or the 4 upcoming bytes. So this is a pretty interesting way of storing data in a very compact format. We have the MoveTo operation here. So if I want to move to X, Y, then of course I want to find out the diff between these. So the actual vector I need to move. And then I will store those 2 bytes and do a relative MoveTo. Nothing strange there. And LineTo, very similar. The only change here is the rLineTo. QuadTo, on the other hand, if we're using this RR-Curve2, is very strange. So first off, we need to have the difference between all of these. So we have the different vectors. And then it's RR-Curve2. So it's a relative curve2. So it's relative to the current position, but each inside is also relative to the previous. So we have dx1 here is the relative there, and then we have dx2 minus dx1, and then we have dx3 minus dx2. And those are the actual values that we put in, and then RR-Curve2. And then we update the current position to the last written position. So that's the Curve2. QuadTo is another operation that many use, and those only have 4 parameters, so it's a very less rounded curve, pretty much. It has less features in it. So what I do is I use a Curve2 and reuse the second 2 one, which is a little bit of a waste in the storage sense, but there is no definition for a quad in the font 1. Then when we want to get the result, if it's defined this format, then we want to close it, of course. So I want to do like that. So if it's not equal to not defined, we want to write these two. So close the path and end the character. And then I want this hex enc here in order to encrypt it. I will encrypt it as a character string encryption. I set encrypt to true. I set the data from the right buffer to the right buffer position. So that's the length of the right buffer I have written so far. And then I will run this char_enc get result as a binary. So this is a way to get back the character string as a binary piece of data. If we now go over to the EEx, this is a program which contains all the characters and all the private information. So what we have here is a bunch of definitions with different configuration values and the char strings. And what I put in here is a bunch of definitions that are very common to this format. We want to define something that is called RD, which is a program to read information from a string. We want an ND in order to set that this is no action define, execute only. And then we want an NP variable that is also short for putting a no access value. And these are used in the char string in order to read and write data. Then we want blue values, and blue values are definitions of different important positions in the font. I haven't really found a specification for it, but I've found other formats that read them in a special way, and I've reused that. Then we have two compatibility features here, min feature and password. Those are defined as this, should be this, is deprecated, but they should be set. And then we want a unique ID here, and I set a unique ID of to this function, and this should be 4 million something, 4 million up to 5 million, because all the others could be used by other fonts that are defined and specified to Adobe, which means that you could read this unique ID and cache information when you have a program. So if you haven't never seen this ID, then you can be sure that you can cache it and reuse it. So I set it to the allowed values. And then I want to create a not defined char string here as well. So I can reuse that whenever we have something that is not defined. I can set the blue values here as cap height and cap x height. So the first value is pretty much the baseline, if I haven't understood it. So, and it's a range of two values. So -15 and 0 is the first range where I think I have the baseline of each character. Then I have a cap height, which is the next two values. So cap height plus 10 value, pretty much. And then I have an x height, which I also set plus for 10. So this is my implementation of blue values. It gets read in correctly when I use it in a font program. Next up, I have a function here to add character strings to this private value. And nothing strange there, just adding more of them. I can get a list of them, so I can actually have the information when I want to put them into an encoding. We will see that later on. I will sort them by the index, so they will come in the right order when I write them out. And then we have the result. And this is getting the string out that should be encrypted. So I create an encoded string here. This is what I want to encrypt. First off, I create this private dictionary with the size of all the definitions +1, because I want to share the strings as well in this private dictionary. So this is a definition of a dictionary. And then I go through each of the definitions. I set the key that we have here, which could be, for instance, RD. So slash and the key, a space, and then the value as a string. And then I write out as a definition after that. So I will define each of these in this private dictionary. And then char string is the last part of the dictionary. And the char strings are also a dictionary with a specific size, of course. And for each char string, I will go through and say this name of this specific char string, /name. And then I will have a space. And then I will get the string of this specific char string. I will write out the length of that string. And then I will use this read functionality So read this many this many bytes afterwards, then a space, and then the string of that many bytes, just encrypted bytes, and then I will have an ND afterwards, so it will define that as a no access define. So this is how we define the char strings. I will end that dictionary. I will end the private dictionary. We will have a read-only and no access put. These are also defined by this format. And then I will have this font name get ext define pop. So I guess that is a way of an extra functionality definition in the bottom. Also something that I found in the specification. And then I will mark the current file as and close the file. So this encoded string, I will create a new hex encoder. I will say that I now I don't encrypt the char string anymore. I encrypt an EExec, and I will encrypt it. So I set the data from this encoded, and then I get the result. And I could be binary here. So if I want to write a binary format, I of course want the result as binary. If I don't want to write a binary format, I will take it as hex. So now we come to the font file, and this is where we specify everything else pretty much. So this could be readable. If you open a font type 1, you can read this data. First off, I have a bunch of definitions up here for font name, paint type, font matrix, font bounding box, unique ID, version, full name, family name, and weight. And then cap height, x height, these are not used anymore. And then ascender and descender, these should be in the metrics. I have never gotten the metrics dictionary to work, or the metrics array, so I haven't figured that one out yet. And then we have this unique ID that starts on 4,000,001, so that's where my font will be. And we have an exec program here that we will use later on, and I need definitions, info. I could have metrics. I haven't used that yet, but I could have. So the definitions that I said here, of course, is the font name. We want the paint type to be 0, and 0 pretty much says that you should fill. I think there is a 1 type as well, where you just write outlines. There could be a couple of more paint types, but the normal use when you write fonts are to fill them. Then we have font type 1. We have a font matrix that I set a default to, and the default, when you have 1,000 square size of matrix, then you need to have a matrix that could move it down to just 1 in order to scale it up again to the right size of your font size when you write something. And then we have the bounding box, which I also set here, and then I will set the unique ID here to +1. And then we have the font version here, where I set 1.3 for the information for that. We have a full name, which I set, a family name if I have one, and a font weight. I set default to medium. That could be, of course, be changed later on. And we will set the font matrix here. So if I get a font matrix, then I will go through that matrix and remove all the commas to spaces, because the font matrix is already in this format, but it's comma separated instead of space separated. So I just replace those, and then I write that string out here, and it needs to be read only. Next up, we have the font box, or the font bounding box. So I write that out as well. Lower left X, lower left I, lower left Y, upper right X, upper right Y. And then I write that out as the font box. And then we could update the weight. I have not done that yet. We could set the below values as cap height and x height. I do that in my implementation. ascender and descender. I don't set those yet. And then we have adding char strings. We can use that in a function as well. And last but not least, we have the result here. So first off, we write out that this is a font type 1 -1 colon 1. So this is the definition of this script up here. Then we will get the definitions of this font name. We'll get creation date, set that out as a specific format. We will set the creator. So currently this is the simple font library that we'll create it. We have a VM usage here where we can set the downloaded size and the extracted size of the full file if we want. I haven't calculated that yet, but that could be used in order to preserve memory when you're actually reading the font. And then we'll create the dictionary or the size of the dictionary +3, because there are a bunch of more things we want to write out. And then I will go through all the definitions, write them out very similar to before. The only difference is the font string, where I just say if it's font name, then I will write that out as just the definition value. Add a slash to it as well. We will go through and write out a dictionary called font info, which will contain all the font info that we defined earlier. Difference here is that we will have parentheses around the different values and write that out. We will write out the matrix here, currently empty, so we will not write out anything in this matrix array, but they are handled similar to the font info. As I haven't figured out how they actually work, they could be working differently, of course. Next, and the last one of the matrix of the different here is the encoding. So this is what we will use the char strings for in order to write out the different name and indexes. So we'll go through here and we'll define an encoding with 256 characters. And then we'll go through that with a for loop here that starts at 0, steps 1 to 251. And for each index, it will write out not defined if it doesn't find an actual value there. So that's a really good way of having all the characters, but all the ones that you haven't defined are not defined. So this is a compact way of saying that. Then we'll go through the char strings here, and if the char string is not defined, if it's not defined, we'll continue. Otherwise, we'll write out the index after a dupe. We will have a space and a slash, and then the name of the font, and then we'll put that into the array. And last but not least, after we've gone through this array, we will do a read-only definition of this array. That ends this current dictionary, and we will start the file of the EExe. That's what we created earlier with all the character strings. So I will create that result here, get that, and I will get a string called clear mark that I will have afterwards. And the reason why I took the first part, which was just the text, the result, and then the clear mark, is because in the binary format you need to separate these. So if we just look at the ASCII format, I will just return these. Font string plus exec result plus clear mark. Very simple. But in the binary format, these are 3 different entities. So first off, I calculate the length of each of these. So the font strings length, the exec length, and the clear length. Then I will create a byte buffer that has the size of all these lengths plus 22. And 22 is just because I need to have a bunch of headers. So the first one is an ASCII one. So we say starting with 128, because this is the binary format. What I will put here is in ASCII. So at 1 is ASCII. Then I will put the length with the most significant byte first. So I will create that first, a byte array of 4 bytes. So this 6-byte header will tell it how long the font string is, and it needs to be exactly the right size, because what it will do after these 4 bytes is fetch all these bytes here in one buffer. And then it will read again and see, okay, what do I have now? Yeah, we have another definition here, and it's a binary one, so a 2, and then the length again, and then I write out the result of that binary, and then it will skip again. So it will fetch this byte array, not even read it or anything, just fetch it, and then it will read again and see, okay, you have an ASCII one, and it should be 1 there, of course, and then the length of that, and then we write out that, and then I have put a bunch of zeros at the end of the file in order for it to have somewhere to end up and see that there is no more in this file. It's not empty, but there is no more to be read. And in the font program that I use currently to read these files in, it expects it to have an ASCII array first, or an ASCII part first, then a binary part, and then an ASCII part. If I don't supply all of those, it's not a valid file, it will just crash. So that's why I have added all of those. So that was pretty much what I wanted to show. We could, of course, look at the test library here just to see how it works. Here I just created a font with the font file, simple font, and then I will create just a box here. So I create this character string, I call it C, I give it the index 67, which is the ASCII index of C, and then I just draw a box all around it, and then I add that character string, and then I add a space here where I don't add anything to it, just the value, and then I write out an ASCII file. So I have a file here, I will get the result, I will not have it as binary, and I write it out. That's the only thing I need to do in order to open it up in FontForge and look at my font with just 2 characters in it. So it's pretty simple to use. I have a more extensive example here as well that you can look at my GitHub repository, where you can read a PDF and move all the fonts over there. I will not go through that in this video. I don't think that is the most common use case. But I think it's an interesting thing to look into, try to understand how these formats work. I might even go in and look at TrueType and figure out how to write a TrueType font and how that is structured and so on. If that is interesting, please leave a comment in the comment section down below. If you like this video, give it a like, share it with your friends and colleagues. I really hope that you learned something today. If you haven't subscribed, please do that, and I really hope to see you in the next video.